Okay. Let's see. Okay, can I go ahead?
Sure, please go ahead.
Okay, great.
Thank you.
Okay, so yeah, today I will talk a bit about model optimization. So optimizing, in this case, artificial neural networks using techniques of quantization and pruning. Very, very roughly, first, this will be done by, in the quantization case, we're aiming to go from, instead of using the standard sort of numerical representation of floating point numbers, to go down to integer types, so quantized discrete integer types to represent our parameters and our data, to be able to gain in inference times and also in resource usage such as memory. And then we will also say a bit about pruning, which is the technique where you try to optimize your architecture and remove unnecessary parts. So you want to trim your network down to the best possible representation for the task you want to do. So I will start by with talking about quantization, go through a bit about how that can be done, and then show a bit of a review of how that looks like in practice, in terms of where you would actually use this sort of hardware-wise. And then we will talk a bit about, from the same perspectives from pruning, say a bit about how it works, and then have a look at sort of a bit of an overview of a review of how it has been used and how it has been shown to bring, well, what type of effects it can bring in different scenarios. And this will be quite of a sort of high-level presentation. So I really hope that you stop me whenever something is confusing or not clear enough, and that we can have a discussion around these things. And then in the end, I would also like to, I think we will have time to have a look at sort of the concrete possibilities you have to apply these techniques using the available frameworks. So in practice, how you would sit down and do some of these things, and what's available there. Okay. So let's just start by just broadly having a view at why this is a good thing to do, or why we need this. So, you know, the situation with neural networks is that we know now how to train and how to use very large models to bring us great results in a number of tasks. And we know now how to train very large models efficiently. And that's good. We can reach great performance. But often in practice, we need to be able to run these models on specific hardware and with specific limitations on, for example, the amount of time we have to perform the inference we need, and the amount of resources in terms of memory or energy usage that we have available to do this. So it's a huge field of interest to be able to make these models as efficient as possible. And these two techniques are two of the large things you can do to be able to do this. And just to give you an overview of what we're looking at here. So this is just a plot of some common architectures, in this case for an ImageNet tasks, so image classification. And size, the area of these blobs correspond to model parameter counts. And I actually zoom out a bit here. We can see that the x-axis here corresponds to flops, or gigaflops, so the number of floating point operations needed to perform one forward inference pass of these models. And on the y-axis here, we have the top one accuracy of ImageNet, so the accuracy on classifying the correct class in a specific image. And we can see that you have these older models, such as the VGG model, which is in some sense very bloated. You have these huge models with hundreds of millions of parameters that reach sort of good performance. But if you compare to these more modern architectures up here, you have hugely more efficient models, which reach very high, a lot better performance than these early large models. And down here to the way left, you have this initial AlexNet model that started the deep neural network era, and so on. So we want to push this. Well, we want to push it down in flops. We want to push models down in size and up in accuracy. So we want to have small blobs up here. It would be very nice if we could achieve that somehow. Okay, so quantization. So we want to see if we can use something else than floating point values to represent model parameters and data, and see how that can help us to improve inference time, how it can help us to reduce memory usage. And then the question is, what type of hardware architectures are available to make use of these quantized representations? And here the situation is that there is some support for this in the GPU world, and there is some tentative and very nice results for how you can use these types of techniques when you have a more flexible hardware, such as field programmable arrays or dedicated ASIC chips, where you have full control over the hardware implementation and where you're not bound to the rules of the standard integer and floating point arithmetic types that you normally have on normal CPUs and GPUs. So just to set the stage, I just wanted to remind you that when we are working in floating point arithmetic, the most usual way we do this is that we use this bit representation of floating point numbers. And normally we do this in either 32-bit or 64-bit representations. And here we represent a floating point number in this exponential form, where we use some of the bits to store the exponent, and we use some of the bit to store the fractional sort of multiplication factor. And then we use one bit for if we have signed floats. So in this way, we have a representation where we can have a large dynamic range of values using only a limited set of bits available. You can contrast this to fixed point arithmetic, where we instead use a representation where we say that we use a particular number of bits to represent something before the decimal sign and something below the decimal sign. So it's the decimal point here is fixed, whereas it floats around in the floating point arithmetic representation. So floating point arithmetic, of course, takes to implement the arithmetic operations using floating point is heavier, or can be heavier, depending on implementation. And fixed point arithmetic can be simpler to represent. in terms of how you implement the arithmetic operations. And this is some of the reason why you can gain a lot by going down to, depending on the hardware situation, going down to this fixed point representation instead of using floating point arithmetic. Right, so normally we stay in the floating point 32-bit world. Can we lower this to lower bit precision in terms of floating point? And can we, and in particular, what we're interested in now is, can we start using integer types? And this, I will abbreviate these types in this way. So FP floating point 32, there are 32 bits, and we're using a floating point representation. And int 8 refers to that we're using an integer type with using 8 bits. Whoop. And there I jumped past the start. So let's. Okay. Okay, so let's start to look at the first and perhaps the most simplest way you could imagine doing this type of quantization procedure. So what you do here is that you start with a model trained in the normal way. You're using floating point values for your data and for your parameters. And when you have finished training such a model, you ask, can I quantize this representation that I have arrived at? So the question is then, can we choose a quantized representation based on those floating point values so that we can still represent the same model? And one way to do this is to simply remap your values, where you look at, for example, if you want to quantize your weight tensor for a given layer, you take a look at your weight values, WI, and you say that, well, okay, I just want to rescale my values to a particular bit width representation such that I can capture the maximum value that is available in that particular tensor. So I rescale with the maximum absolute value of the weight tensor. And I want to multiply that with a factor that represents the largest available number that I have in this fixed point representation, which if I have a signed fixed point representation is 2 to the number of bits minus 1 here. And then we cast this into the, so this last operation here is just casting it into the actual integer type. So we throw away the everything that is not in the integer part. So for example, if you do this with for 8-bit integers, you have explicitly something like this. And if in this illustration here, we see that we have some, in the top line here, you have we have our weight values in this case, if we're quantizing a weight tensor. And we just remap the maximum absolute value down to the maximum available absolute value in the integer representation. So then when we actually, when we use this tensor in our model, we still need to go back to the original value scale when we actually perform the, when we move between layers. So typically when you do this type of technique, you store the quantized value, for in this case in an 8-bit integer array. And then when you perform the final computation over the output of your layer, you would typically go back to the FP32 value scaling by this FP32 scale factor that you computed previously. In this case, for this very simple case, using this max value scaling. So then when you perform an operation, so for example, a convolution or a dense layer, for example, you have in your actual concrete computation some matrix multiplications between these integer 8 arrays, and that can hopefully be performed in an efficient manner on your available hardware. However, it turns out that this very naive way of scaling your values based on max values is a very bad way to do this quantization if you want to retain as much accuracy as possible. You can imagine there being a lot of outliers resulting in that your maximum value rescaling will very poorly represent the majority of the data in the tensor. So I apologize if there is some building going on here in my house. I hope, well, in the apartment above. I hope that doesn't come through too much. So we would want to choose some better method of doing this rescaling to actually represent the values that we have in a better way. And one very nice thing you can do here, which is very simple, is to, instead of choosing the maximum value, you move over to a parameterized representation where you choose some thresholding value. So you say that we don't care about values that are larger in absolute value than this thresholding value. Instead, we clamp them to this value and we say, can we choose this threshold in such a way that we represent the original data as well as possible in some sense. So the question is then how to choose this thresholding value in a good way. So for example, how would you choose this thresholding when we want to quantize the actual, like the input and the activation tensors of our model? And I will now describe one method for how to do this that works out very well in practice, and that is available in a couple of different implementations. So what we do, for example, for an activation tensor somewhere in the model, we take a number of representative input samples, xj. So for example, for an image classification model, this would be a couple of input images. And we create a histogram over the activation values of that tensor over this set of input images. So we simply feed our images through our model. We look at the output tensor that we're interested in to quantize, i.e. to find these quantization parameters. And we see that we get a certain distribution of values. So on the x-axis here is the actual numerical value for this tensor, and on the y-axis is this normalized count number for these values. So this defines some distribution over these values, given these input samples. And if we now choose a certain threshold value, this threshold value t, we will get a different, another distribution, given this thresholding t. And if we want this distribution, given the thresholded value, to be to retain as much information as possible as the original true distribution over the floating point representation, one thing we can do is that we can try to minimize the relative entropy between the integer distribution and the floating point distribution. So what we can do is that we can calculate the Kullback-Leibler divergence between these two distributions, and then try to minimize that over this thresholding argument t. So we're asking for a value of t that makes it so that we lose, well, so that we gain as little information as possible going from the quantized to the floating point representation. So very explicitly, you would go to your histogram here, and you would calculate the corresponding histogram for your quantized thresholded output values, and then you would calculate the discrete version of this integral, and then you try to minimize that over some concrete explicit choices of the thresholding parameter t. So this is an example of how this looks like for this distribution. So now we're in a particular model here. We're in the activations for the sort of fourth bottleneck in a ResNet 152 model. And to the left here is the distribution of activation values, again, over some particular set of input values, some input images. And the white line here, that's indicated by this entropy method, corresponds to this value of the threshold value that minimizes the KL divergence between the quantized and the floating point value distributions at this particular point in the model. So what we do is that we say that, well, all the values that are above this KL minimization threshold value, we simply clamp that to this value. So after we do this transformation, the distribution will look like this. And you see that to the left, we still have the original distribution, and then we have this. So basically all the points to the right here are clamped to this value. So this is this dot here that corresponds to the rest of the values here. So if you do this for a full model, and for this particular realization, this is targeted towards GPUs. So here we are quoting integer 8 results. So when you do this for all the tensors in your model, and you target an 8-bit integer representation. So these are the accuracy results for when you do this quantization on a given trained model for a couple of different models, and in this case using a different number of samples to do this, to calculate these distributions, which are here referred to as this calibration process when you do the quantization. So here you can see that the accuracy loss when you do this type of quantization can, in some cases, for example, here when we're talking about image classification tasks using these large type of models, be quite small. So calibrating this quantization even on quite a few number of samples in this case results in under a percentage drop in accuracy here when we go to this 8-bit integer representation. Okay, so accuracy-wise, we're doing good. We can do this step down, and we can see that we can retain accuracy. How about inference times? How can this help us when we have moved over to this int8 representation? Well, so for example, for a platform where you already have 32-bit representations of your arithmetic, it's usually close at hand to be able to pack and encode this type of 8-bit representation into something where you can parallelize over a number of these operations within your 32-bit pipeline. And this is, for example, what you can do and what is available on some of the NVIDIA-based GPUs, where you can perform theoretically four int8 operations with the same instruction as you would a floating point 32 operation. In practice, you don't get that level of speed up for a number of reasons, but let's have a look at how this behaves. So for the same models as we looked at for when we quoted the performance drop, we can here have a look at how the speed up is compared to the base floating point 32 model, here parameterized over batch size. So you can see that to the left here, you have in this case a Titan X, so a Pascal-based architecture from the NVIDIA GPU line. And this is an architecture that is not specifically tailored for this int8 representation, but you can execute it using using some more efficient representations, but not hardware optimized representations of the int8 arithmetic. And you can see that already here you have some gain in speed. So for example, for a VGG model, you have like 1.5 times 50% speed up compared to the baseline model. But then if you go to something like a more modern line of these GPUs, where you actually have more efficient usage of this int8 representation, you can see that you can gain up to something like almost a 3 times speed up by going to this integer-based representation. And then if you happen to have a problem where you can at inference time do a larger batch inference, that of course helps you to get even larger return in inference speed. Okay. Okay, another thing you can do, apart from this very, in some sense, basic post-quantization, post-training quantization, is that you can ask, is it possible to do better if we do the quantization during training? So to train the model in an already quantized state, and can we there arrive at a better point in weight space for these for the quantized models? So then the question is, if I have a quantized version of, for example, an activation function, how can I handle this when we're doing gradient calculations for our backpropagation, for example? We only have discrete steps here, so the derivative at some point here is either 0 or infinite. So how can we do a gradient descent on this? And one very simple thing you can do is that you simply say that, well, I don't care in the backward path that we're actually doing this in a quantized manner, I will approximate the derivative of the quantized function by its continuous derivative. So this is what's called a straight-through estimator. So basically, we just disregard the quantization when we do the backpropagation step. And in this way, we still get the we still get a quantized model, but we train it using the continuous version of the activation function in this case, for example. So how does this look if we take a bit more look in practice for how you would implement such a thing? Let's see if I can zoom a bit here. So this is the algorithm for a method that's called binary connect. So this was done originally for binary networks, where you go all the way down to a binary representation, but the same type of technique can be applied to any quantization scheme. Let's see, is that a question there? I hear some noise. Okay, I will continue. So what you would do here is that you, in your forward pass, you perform the quantization of your, in this case, weights. So you use your binarized weights to compute your activations, but you keep track of your non-quantized floating points weights as well. So then during backpropagation, you use the values that you have computed during your forward pass using the binarized values, but you compute all the quantities here using the continuous version of the activation functions, for example. And then for the parameter update, so for example, here you see that you're calculating the derivative of your loss with respect to the binarized value, but you assume that in this case that it's actually floating point. And then you typically perform some clipping on that, not necessarily associated with the binarization or the quantization procedure, and then you update your floating point weights and biases based on this binarized value derivative, and then you repeat this process. So in this way, you sidestep this the problem of that you have difficulty computing your derivative of the actual quantized quantities, but you still arrive at something where you can actually train this your quantized model. Yeah, and I should say as well that yeah, well, okay, I guess I did. So basically, this is an implementation of the straight-through estimator. So this is a way to concretely implement the straight-through estimator. Okay, so how does this compare to the post-training quantization procedure that we discussed previously? So this is one result from a recent study on this, where you use a framework that we will also take a look at later, called QKeras or quantized keras, which uses this straight-through estimator method to perform quantization during training. And here also, interestingly, it's in this situation where you assume a variable bit width representation. So we're really looking at how will our model behave when we have this particular bit width representation. So we're moving away from these fixed steps of having only available, for example, integer 8, but we look at integer n representations instead. And to the left here, you can see the comparison between, and we can stay on the level of CPU for now. So the green curve is how the CPU-based quantized model behaves when we go down in bit width. And the dashed line is corresponds to the same model, but using post-training quantization. And on the y-axis here, you have relative accuracy to the baseline floating point model. And so here you can see that the quantization-aware training procedure produces models that can retain accuracy much further down in bit width as compared to a naive post-training quantization. And in this case, this is targeting also hardware where you can make use of this reduced bit width representation, in this case FPGAs. And so to the right here, this is slightly out of scope, but it's just shows that in a reduced bit width representation, we can get away with using much less resources in the target hardware, in this case on the FPGAs. And these are the sort of resources that you measure the usage of in that case. Lots of flip-flops and DSPs. And here is also interesting to note that in this right-hand subplot here, we're also looking at what the situation would be if we did not perform, as in the left-hand case here, homogeneous quantization over the full model. So we're choosing the same bit width precision for all layers in our model, but instead we can also look at what happens if we use a heterogeneous scheme where we choose the bit width dynamically and optimize for that in different parts of our model. And in this case, we're optimizing not to maximize accuracy, but also to minimize energy usage and also to minimize resource usage. So here you can get a model that still retains a lot of your original accuracy, but with very low, as you can see here, resource usage for as compared to the baseline model. So this is so it's super interesting that you can how much there is to gain when you can make efficient use of these representations on your target. Okay, so just to contrast this, so for this, it's always a bit interesting to do. This is it's a fresh field, and it's the comparison wise here is you need to be a bit careful with what you look for. So for example, here when this particular work compares to post-training quantization, they compare to a quite naive post-training quantization scheme. And in particular, it's not this full-blown method of choosing your quantization parameters in a way that minimizes the information loss as we looked at before, but this first sort of level naive quantization scheme, which of course you could argue is not a completely fair comparison. If you try to do a bit of a more directed study on how if you really try to use the best available post-training quantization as compared to quantization-aware training. Now, in this case, for a completely different task, but just to give some perspective on different scenarios here, you can see that for an image classification task, for example, for particular models, you can also arrive at a situation where a well done post-training quantization performs almost, or in sometimes even better than a quantization-aware training for some scenarios. So the situation is not, depending on model size, depending on a task, you can have the situation where you're just fine doing a post-training quantization procedure rather than this full-blown quantization-aware training. But it's certainly the case that for some applications, and in particular for smaller models, the quantization-aware training can be a very effective tool. Right, and this is also just to illustrate that when you do this quantization, you of course have, when you do model optimization in general, you always have a lot of different directions in parameter space for your model to go. So when you do quantization, you want to search over available quantization levels in terms of bit width, but you also want to combine that with your actual architecture, right? You want to say, is this particular architecture I'm using well suited for the quantizations that I want to use? Is it possible to find a smaller architecture or perhaps a larger architecture, but with a heavily reduced bit width that can still retain that can gain more? So starting from a particular architecture and then just quantizing that, of course, doesn't give the full picture of what we can achieve with this method. And that is, of course, something that pruning will target as well. But you can also do these types of searches, or it's very good to do these types of searches over available architectures and quantizations to find a good point in parameter space for your model. So in this case, for example, this work does a search over different number of filters for a convolutional model combined with a search over quantization, and this is for the results for a particular layer, and then you try to optimize for, in this case, a weighted optimization for resource usage in terms of bits and performance of your model. Okay, so in terms of quantization then, and also in general, how does the situation look for hardware support in terms of how much computations we can do for a given allotted amount of power usage in terms of energy usage, in terms of watts, for different segments and for different target scenarios. So this is a very dense plot, but let's just have a look at a few features here. So the legends, the shapes here correspond to the quantization level, the arithmetic representation of the model. So, and here you have all the way down to one bit binary representations and all the way up to floating point 64. You have this distinction between ship, card, and system, and it's just a very rough sort of so system here would be something like a DGX1 training system, which is basically a full large computer where you have a number of GPUs. So you have a full integrated system, and so the power and gigaops pertains to that full system. You have a card, which is then just a single GPU, for example, and then you have a ship, which would be something like an FPGA or just an isolated ASIC. And then you also have a distinction here between the hollow symbols, which are the performance in terms of inference, and then these solid ones in terms of training. So way up here to the right, you have these very power-hungry systems used for training, typically. But that also has the highest available compute power. And then as you move down here, you have these, you have the normal sort of GPU-based cards, but you also have here some of the FPGAs and ASIC, and so the ASICs like these TPUs, and these combined heterogeneous systems where you have ASICs and FPGAs working together. And here you can reach, for example, like this area system here, you can reach quite high high performance for a lower energy consumption level if you compare to, for example, the GPU-based solutions over here. So using and finding models that are efficient for these architectures can give us a lot in this situation. And then down here you have, as we go down in power consumption, you find the dedicated single FPGAs. You have the mobile mobile segment, like the Xavier, NVIDIA Xavier platform, which is also sort of around here that you find where you can have this balance between power usage and performance that gives you something that you can use, for example, say in a self-driving car to perform your the computations needed there. You land somewhere around here. And then you have these very low power systems, which, for example, are dedicated ASICs, but also now you can reach quite high, well, you can do very low power inference even for convolutional models and for some larger models using this FPGAs platform and some available frameworks that we have now to be able to target these platforms more efficiently, which has not previously been available. So this segment down here, I think will have, we will see a lot happening. A lot is happening, and a lot more will happen in the near future. So an example of this is this type of framework that is now available, where you can do these type of quantization procedures targeting, in this case, FPGA targets in a very automated fashion, where you go from the level of, for example, a Python-based trained neural network model, and you go all the way through this framework, and you arrive at an FPGA-based implementation for that particular model. And then you can get results like this, where you can get an extremely low energy usage and the level of just a couple of watts for, in this case, of course, quite small models, but where you can tune this based on your quantization level for your arithmetic to arrive at a very, very good point in this power versus operation plot. Okay. Yes, I think that concludes what I wanted to say about the quantization part. So perhaps, yeah, I will try to poke at if there is someone who wants to ask something now. And then I don't know how you usually do, but if you take, perhaps it would be nice for a couple of minutes break, and then we can go for the great. Okay, so let's move over to pruning. So this is a technique that complements the quantization procedure very nicely. Quantization keeps the architecture, but changes the representation of your parameters and operations within that architecture, whereas pruning asks the question how to find the most efficient architecture for a given task. So very broadly, pruning is the method of trying to remove as much from your model as possible while retaining something that is good enough for what you want to do. And or as Jan LeCun put it, to find the optimal brain damage for your particular problem. And you can do this in a number of different ways. You can imagine a scheme where you try to prune for connections. So you try to find connections that are not important and remove them. And you can also try to have a look at a situation where you actually remove nodes in total from your model. And this very sort of high-level theoretical view of how to do pruning somehow corresponds to what you see in practice when you try to do this in implementation, where you see that you have restrictions for how you can actually perform operations using a pruned model efficiently so that you actually gain something. And so we'll see how that behaves in these different types of scenario of deployment hardware as well. So let's just first take a quick look at the actual at the algorithm of pruning as it is done in a vast majority of cases for the pruning that is done and available in frameworks today. And it looks something like this. So here the pruning is an iterative process where we start with a model that we train to convergence. And then we iteratively try to prune away more and more of this model. And in this scheme here, it's represented as the pruning itself is represented as a mask n that has the same number of parameters, factors as the number of weights in our model. And we represent the pruned model by just multiplying this mask with our weights to indicate where we remove a connection. And this parameterization or this representation of the pruning as something that removes or changes values of weights is what is well, perhaps most common when you look at implementation wise, and you can view the node. Of course, you can view the node removal as a certain type of weight removal as well, depending on how you set your weight values. So you can capture quite a lot by this parameterization of the algorithm. So basically, you prune based on some method. So we haven't said anything about how we do that yet, but we do some type of pruning, removing some set of weights by updating our mask. And then we do a small step of fine-tuning. So we retrain of our pruned model using typically some reduced set or reduced training time, but we do some amount of retraining on the partially pruned model. And then we do this iteratively for a number of steps and remove more and more of the model until we reach some end condition or some fixed number of iterations for this. And this type of scheme, iterative scheme, has turned out to be what works best in practice. So you sort of ease the model into the pruned state. So that's all good and well when you try to look at it from a theoretical perspective and in this general sort of masked situation. But in practice, when you try to do this, you get into this situation where you often have the choice of on what level you want to perform this pruning. So do you want to do this sort of element-wise? Do you want to do this channel-wise? Do you want to do it shape-wise? Or do you want to do it filter or layer-wise? So you can imagine a lot of different ways of concretely of the implementation of this weight pruning, and all of these have different uses when it comes to what type of inference hardware you're targeting. Okay, so just to give one example of a common way for how you decide what weights are good to prune away. A very simple scheme is that you train your model as usual, and perhaps you already have a weight decay as a regularization in your loss function. But if you do not, when you target pruning, it can be beneficial to have this type of weight decay term, which penalizes large values for your weights, and then you simply say that you iteratively remove the smallest weights in some sense. For example, you at each step of your pruning iteration, you remove a fixed number of weights based then on the sorting of weight values. This is a very simple scheme, but it actually works quite well in practice. And then you can get something that looks like this. So here are distributions over weight values, or relative weight values in this case. So we start up to the top left from an unpruned but trained model. And then you train with this added regularization, weight decay regularization. And then you ask, well, I want to keep a certain percentile of my weights. So I want to remove the tail of small weight values. So you just cut off the weight distribution at some certain point, and then you arrive at this pruned version of your model. But just doing the cut gives you a degraded performance. So to regain your performance of your prune model, you do a retraining again with your weight decay terms in your loss, and you again arrive at a situation where you find that you have a tail of small weight values that you can remove, and so you do this again and again and again and again and again and again and again, and finally you arrived at a smaller model. So, for example, this type of unstructured pruning that this is, where you, on a weight by weight basis, try to remove weights based on their absolute value, can give you results like this if you do it on a large convolutional model, for example, as is done in this. This was a very early example of this type of pruning technique, where you also were in this era where you had these types of huge models like the VGG models and AlexNet and models like this, where it turned out that these schemes showed that, well, these models are not very efficient in their in their parameter usage, as you can see from graphs like this, where we look at the amount of parameters that we can prune away versus accuracy loss. And we can see that for this regularized iterative pruning, which is this red curve over here, you can prune away over 90% of your model, and you just have an accuracy drop of 0.5% or something like that over here. So this looked very nice. You could get very efficient models starting from well, it should be said here that now when we do this unstructured pruning here, we get a model where we prune away a lot of parameters, but at this stage it was unclear how this could be used if you try to target effective inference. So you certainly get something where you get lower parameter counts in your model, but if you really want to use this to be able to have for example, a speed up in your inference, it is still unclear how to use this sparsely pruned models effectively, for example, on GPUs. Where for a convolutional model, if you remove some weights in your filters, you still need to perform the actual multiplication when you do that. When you execute your convolutional kernels on your GPU. So even though you have this, in some sense, more efficient representation, since you have reduced your parameter count, it is unclear how you can make use of it in this case.
Hampus.
Yep.
Another question is, why does it work so well? What does this tell us about the energy surface, its properties? Sorry, the loss function surface, its properties.
Yeah. So for this case, I think the general sort of the overall statement is that these types of models, in this case, for these results, they are very large for what they really want to do, and then you also have this very interesting point that I think you might allude to, that it's the case that we can find efficient points in weight space by throwing large models at the problem. So starting from a very large model, you can then find ways down in loss landscape descent to a good point, which you can then sort of prune away to arrive at a high accuracy model.
Yeah, but why can't I just start from a small model, choose the parameters?
Yes, exactly, and that's a very nice question. So for these types of model, it also turns out that it is the case that if you try to do the process of starting from the same architecture that you pruned down to,
yes,
you won't achieve the same accuracy as your pruned model.
So why is that?
Yeah, so there is this interesting hypothesis called the lottery ticket hypothesis, which states that when you have a large enough model, with a random initialization, some part of the model will be in a good state to be able to find an efficient path down in weight space, but typically you need this overparameterization to have the opportunity of finding this submodule that has this property of being in a good place in weight space to be able to find a good way down. But if you then restart from this smaller model with a different initialization, you are not at this good lottery ticket place in weight space, so you won't find the same solution as you did before.
Okay, so I think I remember you pointed this paper out to me 5 years ago, and it's fascinating, but completely unexplained.
Right.
And now it's 5 years old. So I was wondering, has anybody followed this up?
Yeah, there's been a lot of
theory.
work with this.
Did people
Yeah.
try to understand why this is, how this works? Because I
Yeah.
mean, another aspect is that they seem to, you know, they use the initially completely randomly chosen weights, as you may have said.
Right. So
anyway, we can discuss it later, but I'm really interested to know, what have people learned about this since 5 years ago, and is there some understanding now?
right. I will answer that question in 2 seconds. I have some type of contractor at my door here, so if we can pause the recording for 2 minutes, I will.
Yes.
I will be...
Yes.
Yeah.
Anyway, maybe you don't want to discuss all of this now, so we can do it later. But
no, but it certainly has happened quite a few things since the initial sort of lottery ticket hypothesis, and I will get to some of those points later on here as well. But basically, it's I mean, it's still not totally clear what the situation is. If you compare this to, for example, what happens when you use what the difference is between using a smaller model as compared to using a different architecture, which has the same sort of parameter counts as your pruned model from the start, and what that says, and that you can train efficiently, and then what that says about in the context of the lottery ticket is I think yeah, quite interesting.
Yeah.
Okay. Yeah, right. So just to reiterate, this type of weight by weight pruning can reduce your model a lot, but it's a bit unclear how you can use it in the case of, for example, GPU inference. Right. So if we just at this point take a look at sort of what you can do with this type of unstructured pruning when it comes to the large type of models that we have today, the situation looks like something like this. So here are plots of, on the x-axis we have number of parameters for our models, and y-axis top 1 and top 5 accuracy. This is all ImageNet based as well. So for example, orange here, we can follow a standard ResNet, where if you move up in parameter counts, you find this curve of models gaining higher and higher accuracy. And then you can try to prune those models using some pruning schemes, and you arrive at these orange star points. So here it's not, you don't have the association in these plots between which model was pruned, but it's more, the interesting part here is just that we have some method to arrive at models that have a particular model size, and what type of accuracy can we push that to given this procedure, and what does the result looks like there. So for example, for ResNet, you can prune down to something that can pertain quite a lot of your accuracy for ImageNet classification, while retaining accuracy while pruning down in parameter counts, quite an order of magnitudes here. And the same goes for example, your VGG model over here, which is a very much larger model than typically it's a larger model than the corresponding ResNet model for the same accuracy. And then you see that you can prune that a lot. And in this case, you see you also have this situation where, for various reasons, the pruning scheme itself provides a regularization for training. So, and in this case, you even have the situation where your pruning scheme can produce a better model, of course, depending on how you train this model to start with, than your original model. But then here, you can also make this point that, well, if you, as we said just recently here now, that if you start from a particular architecture and then you compare that to a more efficient architecture, in this case, this is a recent line of models that are aptly named EfficientNet. You can see that you can arrive at, you can have models that you can train directly without pruning that has the same, parameter count as the pruned, for example, ResNet models here that achieve the same accuracy. So it's then a question of what in the larger space of total of models in total, is it the case that we can still find some good types of operations and architectures that is possible to train efficiently directly, so that pruning might not be a necessary step. I don't believe that's the case, but it's still interesting to compare in light of when you do this sort of broader search when including different types of architectures as well. Okay, so I think it's nice to say something about the situation for GPUs, since that is what we mostly use. And here, as I said before, it's difficult to implement this per weight unstructured pruning in a way that makes use of the hardware efficiently. We still have to perform all the multiplications of our convolutions, for example. There are no, well, there are no good sparse implementations. It's not the best way to make use of your sparsity to try to do a convolution on the GPU. Let me put it like this: there are some sparse implementations coming up for sparse matrix multiplications, for example, on GPUs that can perform quite well. But in general, you have this problem of that sparse. It's hard to do efficient implementations of sparse operations. So it would be much nicer if we could have some method to prune such that we don't need to change the implementation of our operations of our architecture to make use of it. And one very simple way you can do that in the GPU case is to do channel-based or filter-based pruning. So you can do basically the same thing that we did before, but doing it on a full sort of filter basis, for example. So here you use the same method of training with L1 regularization or L2 regularization for your to introduce weight decay, and then you calculate the total sum of your weights over a full filter, and then you rank your filters based on this sum of filter weights, and then you start to prune away filters based on this ranking. So you remove complete filters from your architecture, and then you do this iterative retraining procedure as before. And since you're removing full filters from your model, you're basically just changing your filter counts, and so you don't need to change anything in the inference implementations, which can give you then a model that gives you a large speed up, since you're using a lot less computation, since you have a lot less filters in your model. And this also works quite well. So just to quote some results here. Here it's parameterized over the sort of speed up of the model in this case, as that can be an important focus when we come to inference. So here you have this type of filter-based pruning, and you see that you have just in the range of a percentage increase in error for almost 3.3 times speed up of your almost 3 times speed up of your model. So it's also reflects then in that you can prune for inference speed using this filter-based pruning, and you can also achieve quite good good speed up ratios for these bigger models. Okay. So then, if you do both of these, well, yeah. So we have, we have 2 methods that perform well. Why not combine them and see how far we can push things? And people are starting to do this and starting to do this in a sort of training-aware fashion as well. So where you do this type of pruning or filter-based pruning together with quantization, and you do that during training, and you try to see how far you can push these schemes. And here is one example of where you have this type of joint quantization and pruning for a model, where you can arrive at a model. So starting from a floating point model that is out here on a scale that consists of, in this case, bit operations. So, but you can just squint and try to look at this as a normal sort of a flops plot. And here you have on the y-axis a totally different measure of model performance that we won't dive into. But the only thing I wanted to indicate here is that starting from a floating point model that is quite large, we can push this down with joint quantization and pruning to something that is orders of magnitude smaller while pertaining model accuracy. And it should also be said that this can now be done in a quite automated fashion, starting from a sort of normal TensorFlow or PyTorch model. So it's starting to become quite available as well. Okay, so I want to take the last time here to sort of dive down and take a look at what's available for how you can do these things in practice in the different available frameworks. But yeah, before we jump into that, I just want to again open for any questions on the sort of introductory parts here to on the pruning parts, if there's anything you want to add there. Well, you can think about that while I switch over to the practical stuff. Okay, so one very interesting framework that has sprung up that enables this type of quantization-based training is what's called Q-Keras or quantized Keras. So Keras, as you probably know, is the sort of meta framework on top of TensorFlow to have a bit of a smoother API that is now also part of base TensorFlow from a while back. And Q-Keras simply creates a layer on top of Keras, or basically re-implements the layers of Keras in using the quantization scheme that we discussed. So using this straight through estimator to do quantization aware training. And this creates a very simple entry point to be able to start to use this, since you can use your standard network definitions, but you just need to swap out. Basically, you add a queue for your layers, and combine that with a configuration of exactly what type of bit quantization you want to perform. So you have control over, for example, the number of bits you want to use, the integer parts of how many bits you want to use per your integer part, and yeah, and you can go down to binary and ternary implementations that uses these more specific efficient representations for those cases where you have the option of doing some smart shifts to, you don't need to be symmetric, so you can stay in a sort of 0-1 range, and then you have some efficiency for the 0 values and so on. So you have particular implementations for that. Then you have quantized versions of your activations, and basically you can do something like this. So you create your model using here exactly the normal Keras layers, and you can train that as normal. So in the quantized case, you would just use exactly same definition. You add in your a queue for your columns, and then you specify how you want to perform the quantization. In this case, they do a stochastic ternary quantization for the kernel weights, and a different quantizer for your biases, and so on. So you can specify that, or do a manual specification of your quantization depth here, and then you just train this model as exactly as you would a normal Keras model. And behind the closed doors here, it's performing this straight through estimator training. So super easy. Yeah, and then you can also use this conversion scheme where if you have a model and you don't want to explicitly use the new class implementations of the quantized layers, you can also do a conversion of an available model definition where internally they change these layers to the quantized corresponding quantized layers. And then I also want to show that these types of frameworks also have incorporated support for searches over the hyperparameters that are the quantization depth, but also the architecture of your model. So here is, for example, what they refer to as auto Q-Keras, where you have a layer on top of Keras where you use some type of hyperparameter searches, such as Bayesian searches, or just random searches, or random grid searches, and things like this. So you can start from a model. You can specify which quantization level you want to search for, so your search space of quantizations. And here you can also target things like if you want to this hyperparameter search to target performance, energy, or a bit width of your total bit usage of your model. And then also, again, you have a very simple interface here to just perform this search over models and quantizations to arrive at a model that optimizes this criteria. So again, super easy entry points if you want to play around with this concretely. Right. Yes, and then of course, it should be said that there is some when you do these types of things in practice for models with skip connections, for example, like a ResNet-based model, you might run into some particular concrete difficulties. For example, if you're doing a search over filter counts, you can't just automatically increase or reduce filter sizes across your model, since you might have incompatibilities with the, for example, if you do an add operation over two paths of different convolutions and you do independent filter scaling of that, you will get incompatible shapes. So you have to be smart about how you do some of these things in practice, but you can do it if you using these libraries as well. Then I also want to show you that you have pruning available in, for example, Keras or TensorFlow now, using this model optimization framework that's available as a standalone package for the TensorFlow case. And here you also have a very straightforward way of training iteratively using pruning, starting from a standard model definition, but where you add in a specific pruning scheme, in this case, polynomial decay, which is just uses this technique of retaining a certain percentage of your weights at each pruning step, but the amount of weights you keep change over time, so that you sort of also converge to a prune model using some particular scheme of how much percent of weights you pertain at each step. And then you just do this explicitly by adding in this callbacks from the model optimization toolkits during your normal training phase. So those callbacks will handle the weight updates and so on. All right. Yeah, and then you have similar functionality available on the PyTorch side when it comes to pruning. Here we can say as well that just to give you an idea of how this is, so support for these types of things are sort of slowly getting into on the framework side. So here on the PyTorch side, you have the availability of this structured pruning, so filter-based pruning, that you don't have available directly, at least as far as I know at this point, using the model optimization toolkit over here. And then you also have sort of slowly it's creeping in the availability of doing quantized training also directly in the large frameworks. For example, PyTorch is starting to implement this this quantized training, but here you can see that it's in the early stages. It does not provide target implementations, for example, for GPUs when you have this quantized model. Yeah, if you want to use these quantized models after you train them, for example, using Keras, you're basically stuck with, well, not stuck with, because it's an amazing path you can take, that you can just take these models and target, for example, FPGAs using different types of libraries. But it's hard to use such a trained model directly on a GPU. But for the GPU case, on the other hand, you have stuff like TensorRT, which is a framework that targets the NVIDIA GPUs. It's partially open source, but this implements a different number of model optimizations that you can run directly on a trained model. So as a post-processing step in the case of TensorRT, where, for example, you can do this post-training quantization using calibration. And the material that I showed you from the GPU-based post-training quantization is based on the publications around TensorRT, which is sort of the framework that has come the furthest when it comes to doing this in practice. And in this case, you're then, of course, targeting NVIDIA GPUs specifically for that. Right. Okay. So actually, that is it. I don't have anything more to add to the base material that I was planning to discuss here. So if there are no questions, that's it for me. But I hope there might be some